أنا بمنزل أحد الأشخاص الآن في مدينة نيويورك، شخص له باع طويل في عالم الكمبيوتر وله تأثير في البرمجة تحديدا. هذا الشخص له يد بعد الله في تطوير لغة الآن تستخدم في أغلب الكمبيوترات وأغلب الأجهزة. هو مطور أو كاتب لغة C++.
Good day, Dr. Strastrup. I'm truly honored to be here and grateful for the opportunity to discuss your invaluable contributions to the world of programming, especially C++. Thank you for welcoming me into your home for this interview.
Okay, welcome. Thanks.
What inspired you to create C++ during its inception? Were you driven by a recognition of a need for a programming language that could efficiently manage memory and provide high-level abstraction, filling a gap in the programming landscape at the time?
Well, that was the conclusion. The problem was that I wanted to build a distributed system. And if I had succeeded, it would have been the first Unix cluster, the first Unix seriously distributed system. And I never got to build this system. There was a lot of reasons for that, but one of them was that there wasn't a language at the time that could do the two things that was necessary for that. If you're building an operating system roughly from the bottom up, you have to deal with hardware and you have to do low-level things like memory managers, process schedulers, device drivers, and such. And there's lots of languages that could do that. And then you have to do the high-level thing, which is trickier. You have to say what a part of a system is and how it talks to another part of the system. And there may not be a memory shared, there may be just a thin wire in between, which means that you have to do network protocols, you have to do communication protocols, you have to make sure that you can communicate without anything being shared, all of that kind of stuff. There was high-level languages that could express these kind of things. Quite a few of them, but not that many. But there was none that could do both.
Yeah.
And so I looked at the languages there were, and my favorite high-level language was Simula, which is where we got classes, class hierarchies, object-oriented programming, object-oriented design came from Simula. And any language that uses the word class to mean type can say thanks to the Norwegians that built Simula. And also it was a nicely, strongly typed language, very, very nice. And it was running 10, 50 times too slow for my use and couldn't deal with hardware. On the other hand, I was at Bell Labs at the time, and down the corridor was Brian Kernighan and Dennis Ritchie. And so C was very well known there, very well supported, and so that's a very good low-level language for the low-level parts. And so I took the class concept from Simula and put it into C, making the facilities run fast enough to be useful at the lower levels of the system. So you can actually do quite strongly typed and quite high-level abstraction very low to the hardware. And that was what I was after. And after working on this for a while, I realized I was doing language design. And as I said, I never got to build this system because it seemed that I'd found a problem and a solution to the problem that served other people's needs also. So people were coming to me and they were starting to use what was called C with classes. And after a couple of years, I had a couple of hundred users, and I had to decide, what am I going to do next? I mean, a couple of hundred users isn't a community that supports a support structure, support, porting, help and such. I was the help desk and everything. And so I either had to make the language better, solve more problems better, or I had to give up. But if I gave up, the people who had trusted me and started using what I was building would be let down. You can't let down your friends like that. That's just not done.
At Bell Labs or other?
It was Bell Labs.
Yeah.
And at the time, there probably was a few people outside Bell Labs, but not many. Most of it was Bell Labs, and the people I knew directly and learned from directly were in Bell Labs. And so I redid the design, re-implemented the implementation, got a real compiler and such.
Wasn't there an IDE at the time, right?
There wasn't an IDE. They came later. Some of the first IDEs were actually in C++ a few years later than that. And we built some of that at Bell Labs, but this was not the emphasis. Maybe the language in the world would have been better if I had spent some time on that. But there wasn't a big team. I mean, till the first compiler was out the door, it was me, and I was writing the documentation and most of the libraries while I was at it. It would have been a good idea, but we couldn't do it.
What aspect of modern software development do you believe is most misunderstood or underappreciated by programmers today?
There's probably not a single one. When you started talking, what popped into my head was the problem of how people view what programming is. Quite a few people think programming is one thing. And you know, programming the guts of an operating system, programming the brakes of your car or the navigation system for your airplane is not the same as building an app for running a shoe store. And a lot of educators don't seem to make the distinction. They want everybody to write code. This is fine. Python was designed for that. C++ was not designed for that. And my primary interest is not to get everybody to write C++. My aim is to make C++ the best tools for people who does sort of engineering level of programming. I want to help the guy that writes the brakes of my car and that kind of users. And C++ is doing very well. People talk about it not being sort of the most used language. It is more used than it ever was in its history, and it fills more of its intended niche than it ever did. But it's not for everybody.
Yeah.
And so I think the answer to your question, what is it they misunderstand most, is that really the field of programming is very, very wide, very, very diverse. And people should respect the fact that nobody knows everything, nobody's an expert in everything, and that the tool chains and languages for programming should be a variety to serve the needs. I mean, numerical programming is very different from GUI implementations.
Especially for embedded systems where the memory resources are limited, C++ is the way to go since it has the ability to go lower to manage the memory much better than other languages like Python or Java, for example.
Yeah, I mean, it's if you actually wrote things in just Python instead of Python calling, say, C++ libraries, the difference in speed is about 70 something. I have seen 200. And the energy consumption is proportional to that, which is not very good if you want to run a large server farm. For Java, 2.5 to 10 times. But of course, you don't actually write the low-level stuff in those languages. Sometimes you call out to C or C++. Sometimes you have special facilities that get special treatment by the JVM or whatever you're calling it. And of course, when you mention the JVM, Java is a C++ application. It runs on C++, just like JavaScript. C++ has a place, and it is not in the hands of everybody, but it is there to help everybody, whatever language they are using. A lot of the more modern languages have a decent performance because of LLVM, which is an infrastructure built for C and C++ in C++. And so if you go and use just about any language, you'll find C++ down near the bottom. This place where hardware meets software has become sort of where I focus.
Looking back on the evolution of C++, are there any decisions or features you wish you had implemented differently?
Well, to some extent, with the benefit of hindsight, I could do every detail somewhat better. But you don't get two chances in this game. And you have to have something that works at the time with the resources available and the knowledge and skills of the programmers available. And I think I got the major decisions right. It's just that I could improve the solutions over and over again. Sometimes I talk to people, sometimes people ask me, and I'm saying, think about it as a time machine. If you had a time machine, you go back and tell sort of the vintage 1980s Bjarne what to do better. What would you tell him? And by the way, remember, a computer in those days had 1 megabyte of memory, and a fast one was 1 megahertz.
Very limited.
Very limited. If you want to fix something in C, like the conversion rules that are fairly anarchic, you have to go back and catch Dennis in 1974 or thereabouts. And his computer didn't have more than 280K of memory. So you can't come and say, I want something with a really good static analysis framework and a guaranteed memory safety and because for starters, you need a computer that's 1,000 times faster and more than 1,000 times as much memory. Evolution means that you start with something and it has to survive, and at each stage along the way it has to be good enough, it has to serve its users, and sometimes you then end up with something that you could do better. I mean, one thing, example, if I had perfect hindsight, I would not have the conversion rules for C. I mean, it's fine to convert an integer to a double, but a double to an integer with truncation, not a brilliant thing to have default. But I would have to have that time machine and go and talk to Dennis before I even joined Bell Labs. And the one thing I probably could have done, if I'd had the design for templates with concepts, the specification of templates requirements on its argument, I think I could have done it back in '88. I could have simplified a lot of things. It was understandable, and neither I nor anybody else at the time knew how to do this. It took us about 20 years to figure out exactly how to do it, and it is so simple. I mean, the requirements are specified as a simple function, and you can ask a type about its properties. Are you a random access iterator? Are you a number? Are you a string-like thing? It's trivial, and it's it's so simple. The current, the traditional templates as we came up with first is just a special case where the only thing you can ask is, are you a type? I mean, type name X. So it'll take anything that's a type. I want to take things that are an input iterator or a random access range or something like that. And honestly, the stuff's simpler today. And so if you'd had the time machine, we could have gotten a better language. But it's a good example. I didn't know how to do it. I knew what I wanted. I wanted something really general. I didn't want to be restricted to just what I could imagine. And I wanted something that was efficient because I had problems with some lower level facilities like C-style array and pointers. I wanted vectors and such to be used, and you could only do that if you're really efficient. And then I wanted decent interfaces. I mean, I was the one who put function argument checking and function argument in function declarations into C. And so I knew the value of interfaces, but I tried and I couldn't do it at the time. I asked every expert I could find how to do it, and I didn't get a good answer. So I had these three things I wanted, and it was quite clear at the time it was not that hard to get 2 out of 3. And so I had to pick the two first I mentioned, generality and efficiency. And then 20 years later, I figured out how to get the third one. And it's now shipping in C++ 20, C++ 23.
The modern one.
The modern contemporary C++ has it. And it works really nicely.
How do you envision C++ continuing to evolve the next decade, particularly in light of emerging technologies like quantum computing and artificial intelligence?
I think if quantum computing becomes major, it will become a box on the side of a computer. So you give questions to the quantum engine, and then you get an answer back. And over there, it's a very different world. Last time I looked at an effective language for that, it was basically physics. If you weren't a good physicist, you couldn't write that kind of code. It's code that has to work forwards and backwards and things like that. It's very alien. I don't think it'll have any real impact on programming, except that you can ask questions now that are much more interesting. But it'll look like a function call. So in that sense, it doesn't affect it. It just affects what you can do and at what cost you can do it. AI, I'm not an AI expert. You can't be an expert at everything, and I've got my tasks done to keep track of what's going on in the C++ world and this area close to the hardware. And so for AI, I think you have some interfaces that are more flexible than what I'm specializing in. People use Python, and it's very dynamically typed, and I'm very much into static typing because I want guarantees for correctness. I want types safety for performance.
Compile times.
Compile times are necessary. I mean, when I was back in the 80s, I was saying, well, there are these languages, say Smalltalk, Lisp, where you can say a lot of things quite easily, and if some things don't work, you find yourself in a very nice debugger. But most of the programs I'm most interested with, there won't be anybody to use that debugger. If the telephone switch in, say, Bogota in Colombia has a problem in late night, there's been nobody there that understands C++, maybe in the other end of town. I want guarantees before I ship the system.
Yeah.
And furthermore, I do want it to run 50 or 100 times faster. And so I focused on something else. Today, we have a similar thing. You write things in Python, and the Python implementation calls some C++ to do the hard work. I was out at the Data Sciences Institute at Berkeley a couple of years ago, and they said, well, you know, I spent 97% of my time writing Python, and my computer spends 97% of its time running C++. The interface is Python, that's what you see, but what is running is TensorFlow or something like that.
Yeah.
And now we're getting hardware that supports it, but the interfaces still has to be something that specifies precisely what is to be done. That'll be C++-like.
Yeah.
You can't just go around and for every operation look at all the possibilities that there might be depending on the input. You have to say, this is the interface, and then you can run it fast.
Yeah.
And so my contribution to AI, if there is any, is to go between the AI and the hardware to mediate that problem. And so, yeah, there's a lot of C++ in all the AI. The vision stuff, the analysis stuff, yeah, there's a lot of it, but it's nothing to do with me really. I'm still dealing with the map from the hardware and a little bit up.
As someone who has played a significant role in shaping the field of computer science, what advice would you give to aspiring software engineers and developers?
Oh dear, it's hard to give advice. Almost as hard as taking advice. I think if you can, get a solid education, get a broad education. Don't think you can specialize as, say, an undergraduate or a high school student. A lot of young students think they know what they need, and they think they know what they want. But as time goes by, the world changes, they change, and the needs change. So if you're specialized, you're sort of stuck. If you've got a good broad education, you can adapt to what you have. So it's not just learning one language. Learn a couple of languages. Don't just learn languages. I'm very keen on machine architecture and some analysis tools and a bit of algorithms. You never know what you need. And then you don't just need to write code. I meet far too many people who think that if they can write code, that's it. What fraction of a time does a developer spend actually writing code? Not all that much. You have to talk to users, potential users. You have to understand problems. You have to learn about new application areas. You have to talk to your colleagues. So many things takes large teams now. I mean, building a video game, for instance, is not a one-person job, and it's not a job that's done by one kind of people. Yes, there are artists of various sorts, there's computer people of various sorts, and you have to communicate around such a group. Yeah. And so you need something that allows you to communicate. So maybe you should read some more literature. Maybe you need to learn a foreign language, if nothing else, English. English is our second language, right?
Yeah.
And I suggest a bit of history to get a background and help understand people. It's not just code. That's where the rubber meets the road, as it was. It's where it gets done to run. But before that, you have to figure out what it is that should run. What is good enough for the user? Sometimes people build brilliant systems that solve the wrong problem. In that case, what failed was not their programming skills. It was their intercommunication skills and their understanding of the world, understanding of problem areas, understanding of people.
With the increasing emphasis on sustainability and environmental impact, do you see opportunities for programming languages like C++ to contribute to more energy-efficient software solutions?
Certainly. About 10 years ago, I started mentioning that my contribution to the fight against global warming was the efficiency of C++, because it didn't use as much energy to get the job done. And the example I used was that if you need another server farm, you have to spend some amount of money. I just looked it up yesterday. It's about $500 million. And it takes the energy of a small town to run it every year. And so I was pointing out that if you needed twice as much compute power to get the job done than with C++, you need another server farm. And since C++ is quite good, it's as good as anything you can find out there, that's the contribution. And I wish for that reason that more of the systems were actually written in C++. The parts that reasonably could be written in C++. There are stuff that's written in far less efficient languages that didn't need to be. And if you want to have fewer server farms, think about writing it in C++ or re-implementing it in C++. Because of the emphasis on efficiency and the emphasis of getting stuff done at compile time, it's very good at energy consumption. Little things like you have you distinguish between dynamically typed languages and statically typed languages. One of my favorite aspects of a statically typed language is that if the compiler or analysis tool catches a bug, you don't have to have an error handler for that kind of bug. Whereas in a dynamic thing, you don't just have to detect the problem at runtime, you have to handle it at runtime. So the code gets more complicated, more bloated, you need a bigger processor, you need bigger memory. So and I realized that fairly early on.
Yeah, it saves energy and cost for the hardware infrastructure.
Yeah. I didn't think about energy when I was first building C++, but I was saying that I want something that can run on a computer I can afford. I remember when I was first implementing the current version of the version that became C++ and was called C++, I was dreaming of getting a 1 megabyte, 1 megahertz computer.
That was your dream?
That was my dream. Oh, yes. And if I got one of those, everything was fine. So I designed the compiler and the runtime and everything to fit into that. And I overshot the target because just about the time I was finishing, Microsoft came out and IBM came out with the original PC, 640K of memory, and it fitted.
Okay.
I had overshot my 1 megabyte target. It couldn't run in a smaller machine.
Do you believe there is a demand for a new high-level programming language that strikes a balance between the performance of C++ and the simplicity of Python?
I don't think such a thing could exist. Python's main claim to fame is flexibility and allowing people to get things done without being very specific. C++'s strength is that you can say exactly what should be done and have the hardware do it well for you. And you build, in C++, if you do it well, you build layers upon layers, and then the compiler collapses it, so it still runs as if you had written the low-level code. I don't think a single language can do that. On the other hand, I certainly hope there will be a language that's better at doing what C++ is doing, but I don't see it on the horizon. You need flexibility, you need efficiency, and either you need a different language for the low level, or you are back in C++'s domain of having to deal with both high level and low level stuff. And that's where the complexity comes. And in the future, it'll become even better at that. It's getting rather good at compile time evaluation. And for computing types at compile time and things like that. So Python is different. It is not higher, it's different. C++ is higher in some areas, Python is higher in other areas, and then we could have a long debate about what high level and low level means in terms of programming languages. I think this is a concept that's overused and quite often misunderstood. The advantages that C++ offer for embedded systems is that it can use the hardware better, and it can provide guarantees before the program starts running, meaning that you can do with less error handling code and more precisely error handling code. Dealing with hardware errors, for instance, is hard, but you can do some of it. I mean, if you look at the modern server farms, often written at C++, you have hardware errors every day. What do you do when a bit just decides it really wants to be a 1 and will never be 0 again? It happens in space probes, for instance. There's nothing like a heavy cosmic particle for creating havoc in your machine. And it happens at every server farm every day. You lose a disk, you lose a processor, you have to recover. So you have to write distributed systems, you have to be really good at concurrency. And C++ for real-world concurrency is one of the best ones there are. And we're working hard on getting it even better.
Parallel processing.
Parallel and concurrent processing. Asynchronous computation and things like that. There's a model that they're working on in the standards committee that I hope to become standard in 2026, C++ 26, the next one coming out. It's already in production use at NVIDIA and Facebook. So if you've used Facebook today, or if you have a video card from NVIDIA, you probably used it today.
Yeah.
It'll be standard, I hope, in a couple of years. It takes forever to get an international standard because everybody has to agree, and you have to be reasonably sure you don't have to fix it again for another 5 or 10 years. Because once it's out there in the whole world, what can you do? You can't fix it. There's no way in a world like that you can just update everything, because there's not a central point for updates. We have, I think, 4 implementations of front ends and a dozen or 2 back ends for different kinds of hardware. You have to get it right. And that can be frustratingly slow, and very frustrating that you have to get agreement with everybody because not everybody agrees with you. Yeah. But that may very well be because they are operating in a field that is not your field, and it's not something you know. The people that does brakes in cars do not have the same constraints for people who does optimal graphics for graphics engines, and they have something similar to the numeric guys, because there's a lot of math in games and graphics these days. But you go through the areas and the concerns are different. And for an international standard, you have to take it seriously. And then, of course, there's different countries on Earth. I mean, we have representatives from all over the world in the committee, and they come from different educational background, different corporate environments, different university emphasis and such. And so it's difficult, but it's very important. I think it's about 7 million programmers, and the standards committee has almost 500 people involved. It's not easy. And it's not a management thing. We don't have rewards. We don't have punishments to get people to work in a particular way. It's not a business.
I attended the GTC 2024. Jensen Huang said, we change the way we write the software, or this will change the way that software will be written using their AI with CUDA or their GPUs. And
yeah,
do you think this truly gonna happen?
At some level it will, and it already has. I mean, C++ and CUDA interact. We have to use the GPUs. One of the reasons, say, C++ works better than some of the dynamic languages is you can handle the concurrency and you can handle the GPUs. Yeah. And one of the things that has happened over the last few years at NVIDIA and AMD and elsewhere is that it's much easier to get data from the CPUs to the GPUs and back again. And that means that you can integrate C++, traditional C++ code with GPU code much easier. It looks more similar than it did 10 years ago. So in some sense it's already happened, but it is one part of the software, one part of the tool chains. It's not everything. The success rate for programming languages is vanishingly small. That is, there's at least 200 languages invented every year and 200 of them die. It's more like one a year worldwide for general purpose programming languages, probably less than that. So you have to be really sure you've got a good problem before you go in there. There's so many people that go in and says, I'll build a better language. Better language for whom? Better language for what? And how would you know that this is a good answer in the about 5 to 10 years before you can use it? Because these days people don't just want a programming language, they want a massive library to go with it. They want an IDE, they want color coding of things, and have a community built up. So we got a whole bunch of them as people needed a community. But it is something that you should only do if you, one, have a problem that isn't solved by an existing language, is likely to still be a problem for you and many, many, many others in 10 years, and something that existing languages can't easily be adapted to.
Like C, for example, to use it.
When I started with C++, one of the design names was that I could use C code. Yeah. Anyway, I didn't want to rewrite, say, Unix. Unix was there, and I would just use it, and the Unix tool chains and such, and they changed and they grew over the years, and turned out to be many other tool chains that fitted the problem. So basically, the answer is yes, it's very tempting to write a programming language, but it very easily becomes either an ego trip or a hobby. Building a language for use of others at a scale where it can support a useful tool chain and community is a very, very hard problem, very hazardous thing to start with. Lots of organizations have done it. I mean, you've seen Google fail, you've seen IBM fail, you've seen Microsoft fail. They also sometimes succeed, but even organizations like that can throw many dozens of programmers and millions of dollars, hundreds of million dollars, onto the problem can fail. So an individual starting should be very careful. And I was just lucky. I found a really important problem, and I found a solution at a time where
To fill the gap
People
between-
didn't see the problem.
Yeah.
I remember talking at Bell Labs, and people just, no, we don't need that. It's just a waste of time.
To build a new programming language.
Yeah, I mean, even though there was users using it at the time, a lot of people didn't see it, and especially management didn't see it. Management, by and large, are not very good at seeing something new. They are very good at managing what exists.
Yeah.
And they can get very conventional, or they sort of get their head stuck in the clouds and they want perfection tomorrow, or they want a grand change. So an evolutionary change is not always easy. So yes, it's very tempting, and I think I could build something like C++, better than C++, as powerful and flexible as C++, with better guarantees than C++, at maybe 1/10 of the size. But I'm not going to do it. I've been tempted many times, and I just... the joke is that if you succeed, you get 10 years of manual labor, which is labor on the manual to the specification. And no, not again.
Okay. I think some companies use Python as a simulator for their solutions, but when they come to production phase, they switch to C++. Is that true?
I don't know. I think so, but I can't think of a concrete example, so I say I think so. It definitely was the case with Lisp earlier, and to some extent Smalltalk. Those were languages that sort of is over in the area with where Python is today. And the problem is that if you use the flexibility of those languages, the dynamic typing of those languages, that's what you need to be able to prototype things quickly. But the results may not actually fit into a well-typed area that allows you to get the performance later. So I think if you want to do that, you have to do, or at least I recommend you do something that's not very popular, which is you build the prototype and then you throw it away, re-implementing from scratch. Because when you re-implement from scratch, you get something that works better, and you even solve some of the problems that has been built into the prototype solution when you were busy thinking about something else. Yeah. And well, we'll see. It's not a popular answer.
What are your thoughts on using AI like ChatGPT to quickly generate complex code in seconds?
I don't really know, but the first examples I have seen has not been promising. That is, you get something done maybe in 1/10 of the time, but it also has 3 or 4 times as many bugs. And now you have to find those bugs and remove them. But that is tedious work, and that is exactly the kind of work you are trying to avoid. And people are very prone to see when it passes the first set of tests, it must be good enough, and then not spend enough time on getting it solid. And so that phenomenon I worry about. The other problem is that you need to train those models. And where do you get the training material? People are using GitHub, for instance, getting all the stuff from the open source community. The problem is a lot of that is low quality, sort of student level kind of code. And the really high quality professional code is not always there. And even if it is, it's drowned out by the endless student projects. I mean, you go onto GitHub and what fraction of the stuff is actually maintained and used, and what are used at scale rather than 10 people. And so where do you get the training material? I think if you could get really good training material for the area of programming that you're interested in, you could get a lot of help from AI. But now we are back to actually where we started, which is programming is not one thing. You don't write the same kind of code for my break as for my website for foodstuffs. And if you just go and you have to get all of this data in for the AI, you are likely to sweep across application areas. You're going to sweep across sort of levels of expertise. Maybe they'll figure out how to solve that problem. I certainly hope so. But as of now, I see that as problems, and I am not at this stage going to encourage use of those techniques in the domain that I'm interested in.
Do you think it's not smart enough to build complex code that has never existed before?
I don't see it. I don't actually see it building a simple piece of code that is good enough up to the best standards today.
Okay, so it generates what has already been generated by other developers.
Because of the training data, it's going to go for the average quality when it doesn't make mistakes. I don't want the average quality for the flight controls of a plane. I want the absolute highest, precisely specified, professionally implemented stuff. Yeah. And actually, I said flight controls. There's very few flight controls that's in the open source. Though I believe the Mars helicopter flight controls are available if you want some high quality stuff.
Have you ever met or worked with Dennis Ritchie during the development of C++?
Oh, sure. I mean, we were in the same center at Bell Labs. I think I had lunch with him most days for 16 years. And we did discuss some things. He was mostly into operating systems at the time, so he was not the main person I was talking to. I was talking much more to Brian Kernighan, his co-author with for the C++, so the C programming language book, and other people there in the lab. But I was definitely part of that community, and I mean, I might talk to Brian again in an hour or so, and do so ever so often. And I mean, that's sort of the greatest expertise in C at the time. Dennis and Brian. There's also Ken Thompson. He was also into operating systems more than I was. One thing that especially beginning programmers tend to underestimate is the importance of a community, a technical community that's supportive, and the ability, if you want to do something new, give a certain amount of freedom to the people developing things. And again, back to the communication issue, you have to have a group of colleagues, group of friends that you can talk serious shop with. And yeah, also good development organizations tend to be in nice places to live, not just the developers, but also their families, and as often near and related with the university. Again, this larger community. I think maybe we should end with the emphasis on community. C++ has grown fairly steadily, except for a period in the late in the very late 90s till about 2005. So you get a growth curve that's like that, and then you get a bend on it about 2000, and then it goes down to 2005, and then it goes up again. And I think it has to do simply with the fact that hardware stopped getting faster single processor speed, and then the ability to deal well with hardware like multi-cores and such, and the ability to write good, efficient code became important again. You couldn't just write your code and wait a year and then the computer would get twice as fast. And so if you avoid that little kink, the C++ growth is fairly steady over the years, and I think it's proportional to the number of problems that fits into its core domain. That has grown. We get more and more gadgets, right? There's computers more and more that uses specialized hardware that is embedded where reliability is needed, where you don't want to use too much memory, you don't want to use too much electricity. You could put in a much bigger computer, but it costs twice as much, and et cetera, that kind of problems. And yeah, I think that's why. And I mean, they talk a lot about the new languages, but usually C++ puts on more developers a year than most of the new languages has in total. I mean, 100, 200,000 more developers. It's shocking. I don't know a really good way of getting really solid numbers with that, but this is the best I hear from people who can count, like the organizations that ship compilers and such.
C++ usually works behind the scenes. For example, YouTube, people will see the website, they see the phone app, but the processing behind the scene for the video, mostly written in C++.
So I was told very recently, Mandalorian, the movie, they used a new technique. So instead of using blue screens, they have basically a video game background that is displayed in 180 degrees around the actors, with projection of everything on it. And if you look at YouTube, there's a very nice YouTube about how Mandalorian was done. And I didn't know that. But they are using the Unreal Engine, which is pure C++. So when you look at, say, your favorite science fiction movie, it's not just the games, it's also in the movies. Yep, you don't see C++, it's right there. It's everything in that thing. The technique differs totally. The acting differs, the way they create the movies differs, and it's all software based. So yeah, C++ is invisible. It's an invisible sort of foundation of just about everything.
Thank you, Dr. Starstrup, for this informative interview. I really appreciate your time, and I wish you a pleasant life ahead.
Thank you, and thank you for spreading what I hope is good information to lots of people. Thank you. I'm pretty sure that camera is running C++. Yeah. Whew. And now we can put the air conditioning on.